So in this section, we want to talk a little bit more about the transition between a liquid and gas. All right. In the past, we've probably assumed that if you're below the boiling point of a liquid, that you would have 100% liquid, and that if you're above the boiling point of a liquid, you'd have 100% gas. All right. This isn't completely true. So let's first start off with a couple of names about the transitions. All right. I can't type in this area right here, so I'm just going to have to have you write these in from me giving you the words. In general, the process of going from a liquid to a vapor is called vaporization. So you can put that right here. And there's two types of vaporization. One that both of these you're familiar with. One type is called evaporation, and the other type is boiling. All right, and there is a difference between evaporation and boiling, and we'll talk a little bit about that. The opposite process is going from a gas to a liquid, all right, and that is called condensation. All right, so first of all, what's evaporation? All right, so we talked earlier about the fact that temperature is a measure of the amount of motion or kinetic energy that particles have. So this shows water down here, and all the water particles have some amount of motion in them. Not all of them have the exact same amount of motion. Remember, the temperature is related to the average amount of kinetic energy. Some are going to have more, some are going to have less, but there's going to be an average. All right. So even at temperatures below the boiling point, all right, there's going to be some of these water. Sorry. So as we were saying, at any given temperature, there's going to be some of these water particles that have more energy or motion than others. All right. So at temperatures below the boiling point, there's going to be a small percentage of the particles that actually have enough motion in them that they can break free from the surface and become part of the gas form above that liquid. All right. So some of them, when it happens, they're going to become a gas particle, which is considered a vapor above the liquid. All right. So this process of the highest energy types of water molecules here becoming part of the vapor is called evaporation. All right. Remember, evaporation can occur at temperatures even below the boiling point of a liquid. All right. So at the same time that this is happening, there are some of these vapor molecules above the liquid that can actually make contact with the top of the surface of the water and become part of the liquid again. All right, and that process is called condensation. All right, so in this diagram, we're going to use a down arrow to represent condensation because that would be the vapor particles becoming the liquid, and we're going to use the up arrow here to represent evaporation. All right. So whenever a liquid is in an open container, the vapor particles can escape the vessel. All right. So the thing is, we're going to have some evaporation going on here, and the thing is, as long as that container is open, the vapor particles can leave the container. All right. So when that happens, that then allows for more evaporation to occur. That's going to replace the water vapor molecules that have left the vessel. All right. So the thing is that things change if you put a cap on the system. All right. If it's in a closed system where the vapor particles can't leave. All right. So the difference is that in this situation, the vapor particles can't escape. All right. And if you do this, once you cap a container, at first you still are going to have more evaporation going on than condensation. All right. But what's going to happen is the evaporated particles are going to start to accumulate in this space here because they can't leave the vessel. All right. So eventually you're going to get to a point where the pace, the amount of evaporation happening is the exact same rate that the condensation is going to be happening. And at that point, you're going to have a constant amount of vapor particles in this space above the liquid. All right. So again, as long as this is uncapped, you have more evaporation going on than condensation because the particles can leave. But when you have it capped, you initially have more evaporation going on, but then you get a certain accumulation of vapor particles. And you're going to have evaporation equal the rate of condensation. All right. So what happens here? All right. Because we've increased the number of gas particles in this space through the process of evaporation, we're going to develop a pressure in that space. All right. And what we call that pressure that results from the trapped vapor molecules is what's called the equilibrium vapor pressure, or just the vapor pressure for short. So first, a little bit about how we measure vapor pressure. All right, it's measured using a device called a manometer. All right, and here's a little diagram of how it would work. All right, you usually have a curved tube containing a liquid. Generally, this liquid is going to be mercury. All right, and you attach some container with the liquid. All right. This end of the tube right here could either be closed or it could be open to the atmosphere. All right. So what's going to happen is the more evaporation that occurs here, the more vapor particles you're going to have in this space here, and the more those vapor particles are going to push down on the top of the mercury right here. All right. So if you have some of these evaporated particles pushing down on top of this mercury right here, that's going to push this side. That's going to push this side of the mercury down, causing this side to go up. And we can measure the distance between those two sides, and that's what that's going to be used to indicate the amount of pressure that gets created by this liquid here. And generally, we measure that in millimeters of mercury. Okay, so a little difference between the vapor pressure under cold conditions versus hot conditions. All right. In both of these situations, we have a capped vessel. But what's going to happen is when the liquid is cold, these particles in the water are not going to be moving quite as fast. All right. So there's only going to be a very small percentage of those water particles that have enough energy to escape the surface and become part of the gas layer above that liquid. All right. By contrast, when it's a hot liquid, these things are moving around a lot faster, and there's a larger percentage of these water molecules at the surface that can escape the surface and become part of the gas. All right. So with a cold liquid, you're going to have a smaller vapor pressure because there's fewer gas particles in that space because there's slower evaporation. When you have a hot liquid, you're going to have increased evaporation, which causes an increase in the number of vapor particles here, which is going to cause a higher pressure. All right. We can graph the vapor pressure on a graph such as this. All right. We're going to put temperature here. We're going to have vapor pressure right here. All right. If you take a regular plastic water bottle, all right, and squeeze the outside, assuming it's not carbonated, you're going to notice it doesn't really feel all that rigid. All right, it's not like you're squeezing a bottle of Coke where it feels like there's a high pressure in the bottle. All right, and that can be explained through this. All right, normal room temperature is only about 25 degrees Celsius. All right, so what's the vapor pressure of water at that temperature? It's below 50 millimeters of mercury. All right, that's a very small vapor pressure. All right, your hand can easily squeeze back against that amount of pressure. All right. But one other thing that this graph indicates is what happens to the vapor pressure if you start to heat the liquid. All right. So if you take that same water bottle that felt kind of squishy when you squeezed it, and you heat it in, say, like some hot water, you're going to notice over time that the bottle starts to feel a lot harder. All right. And so what's going on is as the water inside the water bottle gets warmer, more of the water molecules can evaporate and fill that space above the liquid. Remember, this is something that's only going to be happening if you've got a closed container, meaning you have to have the cap on the water bottle. All right. So also keep in mind that water, even though it's the most familiar liquid to us, is not the only liquid out there. All right, this is an example of two other liquids. All right, this would be pure ethyl alcohol, which is the alcohol that's in beer and wine. All right, and if you had pure ethyl alcohol at room temperature, you'll notice that it's going to have a higher vapor pressure. All right, so this is another liquid right here, chloroform. You're going to see that it has an even higher vapor pressure. All right, so if you had a bottle of chloroform right next to a bottle of water and you gave a squeeze to both of them at room temperature, you notice that there's a little bit, the bottle containing the chloroform is going to feel a little bit harder than the bottle with the water. All right, so interestingly, this has everything to do with something else we're familiar with, which is boiling point. All right, so we mentioned before that liquids can become vapor particles at the surface, even at temperatures which are below the boiling point. So here's a question: if things can become vapor particles at the surface, why can't they become vapor when you're below the surface here? All right. So so the thing is, if something were to become a vapor below the surface of water, it would exist as a bubble. All right. And the thing is, this gas bubble would have a pressure. All right. And what would the pressure inside of that gas bubble be? Well, it would be equal to the vapor pressure of that liquid at that temperature. All right. So let's pretend that we've got regular water at room temperature. All right. Regular water at room temperature is only going to have a vapor pressure of about 40 or so millimeters of mercury. All right. So let's pretend there's a vapor bubble that's trying to form below the surface. All right. The only amount of pressure that it could create is 40 millimeters of mercury. All right. So why don't we see that vapor bubble in regular water? All right. The issue is that we have this atmospheric pressure pushing down on top of the water. All right. So we have a full 1 atmosphere worth of pressure, which is 760 millimeters of mercury worth of pressure pushing down. All right. Well, what if this bubble right here can only exert about 40 millimeters of mercury worth of pressure? All right. This is a lot smaller pressure compared to what's pushing down on the top. And what happens when a high pressure pushes against a low pressure? The low pressure area is going to get squashed. All right. So this area, this bubble right here, this theoretical bubble that wants to exist, can't exist below the boiling point of the water because that bubble can't generate enough vapor pressure to push back against the atmosphere, which is pushing down on it. All right. So what happens though when we normally boil water? All right. Well, most people know that to boil water, we have to heat it up. All right. So what's going to happen to water as you start to heat it up? All right. Well, the vapor pressure of water increases as the temperature goes up. All right. So let's say that you get water up to about 80 degrees. All right. Still below the boiling point. All right. Well, that imaginary vapor bubble that wants to try to exist could only exert about 350 millimeters of mercury. All right. Is that enough to push back against 760 millimeters? No, not yet. All right. It would still get squashed. All right. So we keep on getting hotter, keep on getting hotter, keep on getting hotter. And eventually we get up to the point where the vapor pressure of the water would be 760 millimeters of mercury. So what's special about 760 millimeters of mercury? At that point, the pressure inside of that theoretical bubble would be 760 millimeters of mercury. And that is now strong enough to push back against the 760 millimeters of mercury that the Earth's atmosphere is pushing down on the surface of the liquid. So that bubble can now exist. It can push back and not get squashed by the forces that are normally squashing it. All right. So the thing about boiling point is that it's normally reported at sea level, because what we're interested in is